Your desk, maybe your coffee cup, or even just think about yourself, everything seems so solid, so definite.
Right. Undeniably real.
Exactly. And yet, we know, or we're told, that underneath it all, the universe is built on these incredibly bizarre, probabilistic quantum particles.
Mm-hmm.
So how does that happen? How do we get from that quantum weirdness to, well, this, our stable, predictable reality?
And that question right there, that's the absolute core of what physicists call the measurement problem.
Okay.
It's arguably the deepest, maybe the most challenging question in physics today. And it's not just philosophy either.
Right.
So in this deep dive, we're going to dig into the sources you've gathered, really try to unpack this gap, this chasm between the quantum world and the classical one.
Pulling out the essentials.
Yeah, exactly. The mission is to kind of give you a shortcut to understanding why your reality looks and feels the way it does.
Okay, sounds good. So let's maybe start where it all began. The world we thought we knew.
Classical physics.
Right. For centuries, that was it. The clockwork universe, Newton, Laplace, that whole picture.
Mm-hmm.
And the core idea there was just pure determinism, wasn't it?
Absolutely. If you knew everything about a system, like every tiny detail.
The exact position, the exact speed of every single particle.
At one specific moment, then boom, you could theoretically predict its entire future. And its past, for that matter.
That's Laplace's demon, right? That imaginary super intellect.
Exactly, seeing everything past and future. But here's the interesting bit, the kicker maybe. Even that classical world wasn't quite as perfectly deterministic as we sometimes think.
Oh, how so?
Well, the sources point out that if you look really closely with scrupulous examination, classical mechanics actually has these weird spots, these pathologies.
Pathologies, like theoretical breakdowns.
Sort of, yeah. Situations where predictability just fails, even within Newton's own rules. Think of things like space invaders, hypothetical particles just appearing from infinity with crazy speeds.
Appearing out of nowhere.
Theoretically, yes. Or there's John Norton's dome, a famous thought experiment. You have this perfectly smooth dome, a ball balanced right at the very top.
Okay. Frictionless, I assume.
Perfectly frictionless. Classical physics says it can stay there forever, but it also says it can just spontaneously start rolling down.
Spontaneously.
Without any push.
Without any cause. In any direction. The equations allow for it.
Huh.
Yeah.
That's weird for classical physics.
It is. And it highlights this hidden assumption in the classical view, this metaphysical assumption, the sources call it, that you can have infinite precision in measurements and initial conditions.
Which you can't in reality.
Right. So the big shift to quantum mechanics, it wasn't really going from perfect certainty to pure randomness. It was more like shifting from a system where unpredictability was seen as a kind of flaw, something that happened in weird edge cases.
Like the dome.
To a system where indeterminism is actually built in. It's fundamental.
Okay. And in that old classical world, an object itself, its very nature, its ontology was clear-cut. Very clear. It had definite properties. Position, speed. These things existed objectively.
Whether you looked or not.
Exactly. That's counterfactual definiteness. It's what Einstein was getting at famously with the moon. He argued the moon has a definite position.
Even when no one is looking at it.
Precisely. It just is. Solid, real, independent of us.
But then, bam, the 20th century happens. Quantum mechanics arrives.
And turns everything upside down. That predictable clockwork, gone. Replaced by a reality fundamentally built on probability and, well, uncertainty.
So let's get into that. What's at the heart of this new quantum picture?
At the very heart is the wave function, usually written as CI, the Greek letter.
Okay.
Think of it as the ultimate description. It contains all the information that it's possible to know about a quantum system.
Everything.
Everything knowable, yes.
Oh.
And when it's left alone, its evolution over time is described perfectly by the Schrödinger equation. And this equation is crucially linear.
Linear, meaning combinations of solutions are also solutions.
Exactly. And that linearity is the mathematical root of a lot of the quantum weirdness.
Like superposition.
Precisely. That's one of the key pillars, superposition. Because the equation is linear, if a system could be in state A and it could be in state B, then it can also be in a combination of both state A and state B at the same time.
Okay, hold on. Not just that we don't know which one it's in.
No, that's the critical difference from classical ignorance, like hiding a coin. It's not hidden heads or tails. It's in a state that is genuinely both, simultaneously, until you measure it.
That's the basis for quantum computing, right? Qubits being 0 and 1 at once.
Absolutely. That's pillar one. Pillar two is wave-particle duality. Quantum things, electrons, photons, whatever, they aren't just particles and they aren't just waves. They're both somehow.
Depending on how you look.
Kind of. The classic demonstration is the double-slit experiment. Send electrons through one at a time.
And you get an interference pattern, like waves would make.
Right. Even though each electron arrives at the detector as a single localized particle.
Yeah.
It acts like a wave passing through both slits, interfering with itself, but hits like a particle.
Mind-bending. Okay, what's the third pillar?
Heisenberg's uncertainty principle. This one's famous.
Yeah.
He says there's a fundamental limit, an absolute limit on how precisely you can know certain pairs of properties at the same time.
Like position and momentum.
That's the classic pair. The more precisely you know where something is, the less precisely you can know its momentum, and vice versa. And importantly, this isn't because our measuring tools are clumsy.
It's not an equipment problem.
No, it's baked into nature.
Yeah.
It's a direct consequence of that wave-like nature we just talked about.
Yeah.
These aren't just like random weird rules. They all emerge logically from the mathematical structure of the theory, Hilbert spaces, operators, all that.
Okay, so we have this wave function encoding all these possibilities, these superpositions, this inherent uncertainty. But then we look, we do an experiment, we measure something.
Mm-hmm.
How do we get from that wave of possibilities to the single definite result we always see? You know, the electron hits here, not smeared out.
That critical link is the Born rule, named after Max Born.
Okay.
What it says is that the square of the wave functions amplitude, basically. How big the wave is at a certain point gives you the probability density of finding the particle at that point if you make a measurement.
Probability density. So where the wave is bigger, it's more likely to be found.
Exactly. It's like a probability forecast. It puts probability right at the foundation of physics in a way it never was before.
How's that different from, say, flipping a coin? That's probabilistic.
But classically, the coin flip's probability comes from incomplete knowledge.
Yeah.
If you knew the exact forces, the spin, the air resistance, you could predict heads or tails perfectly.
Right. Deterministic underneath.
But in quantum mechanics, even with complete knowledge knowing the wave function perfectly, you still only get probabilities for measurement outcomes. This isn't incomplete information. The sources call it ontological uncertainty.
Ontological. Meaning uncertainty about what is, not just what we know.
Precisely. The property itself, like position, is genuinely indefinite before you measure it. That's a huge monumental shift from the classical world.
And this right here, this must be where the big conflict comes in, the measurement problem itself.
You got it.
Because if quantum mechanics describes everything fundamentally, then it has to explain our everyday classical world too. Tables, chairs, us.
Mm-hmm.
But if the basic state is superposition, why don't we see superpositions of tables and chairs? Why does measurement seem to force a single outcome? That's the deepest puzzle, as the sources put it.
That's exactly it. The measurement problem stems from what the sources call a fundamental inconsistency, right in the standard way we teach and use quantum mechanics.
An inconsistency in the rule.
Yeah, it basically gives us two different contradictory rules for how a quantum state changes over time.
Two rules? What are they?
Okay, so we have the two evolutions. First, there's unitary evolution. This is the smooth, predictable, deterministic evolution described by the Schrödinger equation. It applies when a system is isolated, left alone, it's linear, and it preserves superpositions.
Okay, the normal quantum evolution.
Right. But then second, there's wave function collapse. This is also called the measurement postulate. It says that when you measure the system, something totally different happens. The wave function suddenly, randomly jumps. It's abrupt, it's nonlinear, and it goes from that superposition of possibilities to just one single definite state, the one you actually observe.
And that's just stated, like an extra rule tacked on.
Pretty much. It's not derived from the Schrödinger equation. It's an additional postulate. And the huge problem is, the standard theory gives no clear, unambiguous principle for when Rule 1 stops and Rule 2 takes over. What even counts as a measurement?
Okay, I see the clash.
Yeah, you can frame it really rigorously, as the sources do, using the logical incompatibility of three fundamental claims.
Okay, what are the three?
Claim 1, the wave function is a complete description of the system. Claim 2, the wave function always evolves according to the smooth, unitary Schrödinger equation. Claim 3, measurements always have single definite outcomes.
And they can't all be true.
Logically, no. You can have any two, but not all three. Our everyday experience screams that claim 3 is true. We see definite outcomes.
Right. The cat is alive or dead, not both.
Exactly. So that forces us to question either claim 1, maybe the wave functions in the whole story, or claim 2, maybe the Schrodinger equation isn't always right. Maybe collapse is real. That's the core tension.
And to really drive home how bizarre this gets when you scale it up, there's that famous, slightly morbid thought experiment.
Poor cat.
Yeah, poor cat. Schrödinger's cat.
Yes. Schrodinger came up with this in 1935, explicitly as a burlesque case, he called it, to show the downright absurd places you end up if you blindly apply the quantum rules to everyday objects.
So the setup, cat in a box.
Right. Field box, inside. A cat, a tiny bit of radioactive material, a Geiger counter, a hammer, and a flask of poison.
Sounds ominous.
It is. If a single radioactive atom decays a quantum event, the Geiger counter detects it, which triggers the hammer, which breaks the flask of poison.
And curtains for the cat.
Right. But if the atom doesn't decay, none of that happens, and the cat remains alive.
Okay, so the cat's fate depends on a random quantum event.
Exactly. Now, according to quantum mechanics, before we observe it, that single atom is in a superposition of decades and undecades.
Okay, standard quantum stuff for an atom.
But because the Geiger counter, the hammer, the poison, and the cat are all linked, entangled with the atom's state, the entire system, including the cat, gets dragged into this superposition.
You mean the cat is in a superposition of?
Simultaneously alive, AG, dead, according to the math.
Which is absurd. We never see that.
That's the whole point, the paradox. We open the box, we make an observation, and we see a cat that is definitively one or the other. Alive. Or dead. Not both.
So the act of looking, the measurement, seems to force the wave function to collapse into one reality.
That's the standard story, yes. But it just deepens the mystery, as the sources say. What is that observation?
Yeah, that's always been the fuzzy part for me. What is an observer? Does it need consciousness? Can my cat observe another cat?
That's the elusive observer problem. It's a great question. Early on, some people, like Wigner, did speculate about consciousness playing a role.
But that's not the main view now.
No, that's largely rejected. The sort of working consensus is that a measurement is basically any interaction with a large enough macroscopic system that creates a stable, irreversible record of the outcome.
So the Geiger counter clicking could be enough. It leaves a record.
Potentially, yes.
Yeah.
But then you hit another problem. If the Geiger counter itself is made of quantum particles, shouldn't it also go into a superposition? A superposition of click dude and not click dude entangled with the atom.
And then if I look at the counter.
Then you become entangled. This is the von Neumann chain, or Wigner's friend paradox.
Yeah.
You can keep pushing the point of collapse further and further back. Where does the quantum description stop and the classical world begin?
So it's not really about consciousness per se.
Probably not. The real issue seems to be this transition from the microscopic quantum realm to the macroscopic classical realm we experience. That boundary is the puzzle.
Okay, this feels like we've hit a bit of a wall. How does anything ever become definite?
Well, hold on. There is a really important physical process that, while maybe not solving the entire measurement problem, goes a huge way towards explaining why the world looks classical to us.
Okay.
This is where we move from pure interpretation debates more towards physics we can actually test and calculate.
That sounds promising. What is it?
It's called quantum decoherence.
Decoherence, okay.
The key insight is simple but profound. No real-world system, especially a macroscopic one, is ever truly isolated. It's constantly bumping into things.
Like air molecules,
Yes.
photons, vibrations.
Exactly. It's interacting with its environment nonstop. And this incessant and unavoidable monitoring by the environment, as one source puts it, acts like the engine that washes away quantum weirdness and makes things look classical.
How does that work? How does bumping into air molecules stop a cat being alive and dead?
Okay, so think about entanglement as the engine. When our quantum system, let's say Schrödinger's cat, in its superposition, interacts with even a single particle from the environment, say an air molecule bouncing off it, they become entangled.
The air molecule gets linked to the cat's state?
Yes. An air molecule bouncing off the alive part of the cat's superposition becomes correlated with alive cat. One bouncing off the dead A part becomes correlated with dead cat. Now, repeat that. Billions upon billions of times per second with countless air molecules, photons, everything.
Okay, so the environment gets tangled up with the cat's superposition.
Massively tangled. Information about the cat's superposition, the delicate phase relationship between the alive A and dead states that allows them to be a coherent quantum superposition, gets leaked or spread out into the environment, it gets encoded in the states of trillions of environmental particles.
So the coherence isn't destroyed, just lost, diluted.
Beautifully put. It's distributed across the trillions of degrees of freedom of the environment. It's still there, in principle, in the total wave function of cat plus environment, but it's incredibly scrambled and practically impossible for us, who are only looking at the cat, to ever retrieve or detect.
So what does that look like mathematically for just the cat?
Mathematically, we use something called the reduced density matrix. We basically average over or trace out all those environmental degrees of freedom we can't track. When you do that, those crucial off-diagonal elements in the matrix, the terms representing the quantum coherence between alive and deady.
The superposition bits.
Yes, they decay with astonishing speed. They effectively vanish from the cat's description alone. What's left looks, for all practical purposes, exactly like a classical probabilistic mixture. A 50% chance the cat is alive and a 50% chance it's dead. Not both at once anymore.
It appears to have collapsed.
Exactly. It looks classical. And this process has a quantitative basis. The rate of decoherence depends strongly on the size of the superposition, the mass of the object, the separation between its superimposed states.
So for tiny things, it's slow.
For an electron in the double-slit experiment, decoherence can be minimized. But for a macroscopic object like a cat or even a dust mote,
Billions and billions of atoms.
the interaction with the environment is so strong that decoherence is immense and almost instantaneous, faster than any possible measurement we could make. That's why we never see macroscopic superpositions in everyday life. The environment is constantly measuring them, forcing them to look classical.
Wow. Okay. And does this also explain why we see things in definite positions usually, not superpositions of speed or something else?
It does address that too. That's the preferred basis problem. Decoherence naturally picks out certain properties because interactions with the environment, like photons scattering off an object, depend very strongly on the object's position. Position is the property that gets most robustly and constantly monitored. So superpositions of position decohere incredibly quickly. Other kinds of superpositions might last longer, but position states are the most stable against environmental interaction. This is called environment-induced superselection, or inselection. The environment selects position as the classical property we perceive.
Okay, decoherence sounds incredibly powerful. It explains why we don't see cats that are both alive and dead, why my desk looks solid and stays put. That feels like a massive piece of the puzzle.
It really is. It's become a central part of understanding the quantum to classical transition. It explains the appearance of classicality in underlying quantum mechanics.
You said earlier it doesn't fully solve the measurement problem. What's still missing? If decoherence makes it look collapsed, isn't that enough?
Here's the absolutely crucial point. Decoherence explains why we don't observe interference between the different possibilities, like the live cat and the dead cat. It explains why they behave like separate classical alternatives.
But
within the math of the total system, the universal wave function, including the environment, both possibilities, live cat entangled with its environment, dead cat entangled with its environment, are still there. Decoherence doesn't actually eliminate any possibilities. It just makes them practically unable to interfere with each other from our perspective.
so the wave function never really collapsed, according to decoherence alone.
Not in the sense of one outcome vanishing. It just branched and got smeared out into the environment. So the problem shifts. It's no longer what causes the collapse, but rather,
Why do I only experience one of those branches? Why does my perception, my reality, correspond to only the live cat or the dead cat if both are still technically out there in the universal wave function?
exactly. You've nailed the remaining core of the measurement problem. Decoherence explains the emergence of classical probabilities, but not the emergence of single definite outcomes for individual observers. And that is where the different interpretations of quantum mechanics come into play. They try to answer that final question.
Right. So to get the full picture, we have to kind of pick a side. Choose an interpretation that fills that final gap.
Essentially, yes. And these interpretations aren't just, philosophical flavors. They propose different fundamental pictures of reality. They each tackle that contradiction we talked about: wave function, completeness, unitary evolution, definite outcomes, by challenging one of those assumptions.
Okay, can we quickly run through the main ones? How do they solve this?
Sure. Let's start with the oldest, the Copenhagen interpretation. Think Bohr, Heisenberg early on.
The standard textbook version, often.
Right. Its solution is basically to postulate a fundamental dividing line, a cut, between the quantum world and the classical world of our measuring devices. When a quantum system interacts with a classical measurement device, Collapse just happens. It's a
It
postulate.
just does. No mechanism.
No mechanism offered within the interpretation itself. Classical reality exists because our instruments are classical and for its outcomes. Its weakness is precisely that vagueness about the cut and the fact that collapse is just added on. It's ad hoc.
Okay, what else?
Then you have the complete opposite extreme, in a way. The many worlds interpretation, MWI, pioneered by Hugh Everett.
The sci-fi sounding one.
It does sound like sci-fi. MWI's solution is radical. There is no collapse, ever. The Schrödinger equation always holds true for the entire universe.
But we see definite outcomes.
MWI says that every time a measurement could happen, the entire universe splits, or branches, into parallel realities, one for each possible outcome.
So the cat is alive in one universe and dead in another universe that just branched off.
Exactly. And the observers in each branch also split, so the you in one branch sees a live cat, the you in the other sees a dead cat. Decoherence explains why these branches rapidly become isolated and can't interact.
So our classical reality is just one branch among countless others.
An astronomical number, yes. Its strength is its mathematical elegance, just the Schrödinger equation, no extra collapse postulate. Its challenge is what people call ontological extravagance. Do we really need infinite parallel universes? Plus, properly deriving the Born rule for probabilities from this picture is surprisingly tricky. If all outcomes happen, where does probability come from?
Okay, what's next?
Bohmian mechanics, also known as pilot wave theory, from David Bohm. This one challenges the idea that the wave function is a complete description.
It adds something.
Yes, it adds hidden variables. Specifically, it says particles always have definite actual positions, even when we're not looking. The wave function still exists, but it acts like a pilot wave that guides the particles along deterministic paths.
So particles have real positions, and the wave tells them where to go.
Kind of like that, yes. In this view, classical reality is the only reality. Things always have definite properties. The apparent randomness of quantum mechanics just comes from our ignorance of the particle's precise initial positions within the wave.
So it brings back determinism in a sense?
It does, but at a cost. Its main challenge is that it's explicitly non-local. The pilot wave can transmit influences instantaneously across vast distances, which Einstein called spooky action at a distance. Also, the status of wave functions for paths where the particle is a bit strange. These empty waves still exist and affect things.
Okay. Non-local. Spooky. One more.
The last major category is objective collapse theories. Think GRW theory, Girardi-Rimini-Weber, or CSL, continuous spontaneous localization, or Roger Penrose's ideas about gravity causing collapse.
Objective collapse, meaning collapse is real, not just about observation.
Exactly. These theories challenge the idea that the Schrödinger equation is always perfectly correct. They actually modify it. They propose that wave function collapse is a real physical process that happens spontaneously, randomly, all the time, but very rarely for single particles.
Spontaneous collapse.
Yes. The idea is there's a tiny probability per particle per unit time for its wave function to suddenly localize. For one particle, you'd wait maybe hundreds of millions of years for it to happen.
Practically never.
But if you have a macroscopic object, like our cat, with trillions upon trillions of entangled particles,
then the tiny probabilities add up.
they add up dramatically. One particle collapsing can trigger the collapse of the whole entangled system almost instantaneously. So these theories predict that the fundamental laws themselves actively suppress large-scale quantum superpositions. Classical reality emerges naturally because quantumness gets automatically switched off for big things.
That sounds plausible. Does it have drawbacks?
The main challenge is finding the right modification. There are different models, but the huge advantage, and what makes them scientifically exciting, is that they make new, potentially testable predictions.
Oh, unlike the others.
Mostly, yes.
Yeah.
Copenhagen and many worlds and their basic forms don't predict any deviation from standard quantum mechanics. Bohmian mechanics matches standard predictions too, though its implications are different. But objective collapse models predict tiny spontaneous energy releases or heating due to the collapse process, or slight deviations from quantum mechanics for very large systems. They are, in principle, falsifiable.
Which means we can actually test them. That's huge.
It really is. And that leads us directly to the experimental frontier. People aren't just debating this in armchairs. They're in labs trying to push the boundaries.
Trying to see quantum effects in bigger and bigger things.
Exactly. The goal is to probe the quantum classical boundary. Can we create and maintain quantum superpositions in systems that are getting closer and closer to our everyday macroscopic scale? Can we build macroscopic Schrödinger cats, essentially?
What kind of systems are we talking about?
Really amazing stuff. Things like tiny mechanical oscillators, think microscopic vibrating drum heads or cantilevers, containing billions of atoms that have been cooled near absolute zero and put into quantum superposition states, even entangled.
Billions of atoms in superposition.
Yeah. Or experiments with nanocrystals, again containing maybe up to 1 billion atoms, put into spatial superpositions, being in 2 places at once. There are also superconducting quantum interference devices, or SQUIDs. These are circuits where you can get macroscopic electrical currents involving billions of electrons flowing in a superposition of clockwise and counterclockwise directions.
That's incredible. What have these experiments shown so far?
Well, first, they've confirmed decoherence theory with remarkable precision. They can literally watch the quantum superposition decay into a classical-like state as they controllably couple the system to an environment. It shows that smooth transition predicted by decoherence.
So decoherence definitely happens.
Oh yes, that's well established. They're pushing the size limits constantly from hundreds of thousands of atoms to trillions. There are even serious proposals, as mentioned in the sources, to try and detect quantum effects in the 10-kilogram mirrors of the LIGO gravitational wave detectors.
Wow. Kilometer-scale experiments potentially showing quantumness in human-scale objects.
That's the ultimate dream for some of these tests. And crucially, this work directly tests the objective collapse models.
How so?
Because those models predict that collapse should happen spontaneously and faster for larger objects. So if an experiment manages to create and maintain a quantum superposition of a sufficiently massive object for longer than a particular collapse model predicts is possible.
Then that model is wrong. It's falsified.
Exactly. These experiments are putting increasingly tight bounds on where collapse could be happening if it's a real process. They're ruling out parts of the parameter space for these models.
Are they also looking for those side effects, like the heating?
Yes, those are the non-interferometric tests. They look for the subtle side effects predicted by collapse, like a tiny constant background noise or slight heating, even at absolute zero, caused by spontaneous collapses happening.
And have they found anything?
The sources say that no such effects have been detected to date, which doesn't disprove collapse theories entirely, but it puts increasingly stringent constraints on them. It makes the window for where these effects could be hiding smaller and smaller.
Okay, so wrapping this all up, what does this mean for, you listening right now, for your solid-seeming reality?
Well, the big takeaway is that quantum decoherence does an amazing job explaining why the world appears classical to us, why things look solid, why they have definite positions, why we don't see macroscopic weirdness. It averages out the quantum fuzziness through constant environmental interaction.
It sweeps the quantum weirdness under the rug, so to speak.
That's a good way to put it. But it leaves that rug kind of lumpy, because underneath, all the possibilities might still exist in the universal wave function. So you're still left with this choice, this enduring enigma, as the sources call it.
A choice between interpretations to explain why we only experience one definite outcome.
Right. Do you accept the many worlds? Does the wave function collapse via some unknown mechanism? Maybe linked to observation, like Copenhagen suggests? Or spontaneously, like GRW proposes? Or are there hidden variables, like in Bohmian mechanics? Currently, multiple, mutually exclusive interpretations can account for the data we have.
So the choice comes down to fundamental questions. Is the universe deterministic or probabilistic? Is the wave function physically real or just information? Is there one reality or many?
Those are exactly the kinds of deep questions it forces us to confront.
And it feels like the deciding vote might come from those experiments pushing the boundary.
That's the hope. As technology improves, allowing us to create and probe ever larger and more complex quantum systems, maybe we'll finally see a deviation from standard quantum mechanics or find evidence that definitively supports one interpretation over the others. Maybe we'll find the noise from objective collapse, or maybe we'll keep pushing the boundary further and further, making many worlds or Bohmian ideas look more plausible.
It's fascinating. This isn't just some abstract physics problem. It's about understanding the absolute bedrock of reality, the fabric of the cosmos.
And our own place within it. How does consciousness, observation, and the definite world we experience emerge from this weird quantum substrate?
So the final thought for you is, what new discoveries just around the corner might completely change your understanding of reality? The quest continues.